screen if I remember how to do that. All right, so first I want to give a quick overview of just Roman and at a very, very high level, give an overview of the exoplanet science. I'm very biased in this version of this Roman talk because I'm an exoplanet scientist by trade. Looking online, looks like most of y'all are planetary scientists, exoplanetary folks, astrobiologists. So apologies if I go into sort of page, but feel free to interrupt if you have any questions or if I'm explaining something that you'll already know. I don't want to waste your time as well. But thanks again for having me. Really appreciate it. So I'm going to start with a quick sort of primer overview of Roman and get screen sharing going. Doop and doop. So the Roman Space Telescope, this is NASA's next flagship astrophysics mission. This is launching in as soon as next fall. So it's launching no earlier than October of 2026 and no later than May of 2027. And Roman is on schedule, on cost, so it's on budget, and things are going really well. It's currently being integrated and tested out here at NASA Goddard out in Maryland in Green Bank. Right now, there's been lots of mission and really specifically hardware milestones as well of integrating everything together, testing it, and we're marching right along to having it. I think the last I've heard is we're on schedule as well for a fall 2025 launch. So it's a pretty exciting time. If you have the opportunity to come out to Goddard and see it, it's pretty incredible to see it being built in real time. Right now, we have some components that are doing thermal vacuum chamber testing. Other parts are basically doing integration and testing to make sure everything has been wired up correctly and we're receiving signals as expected. So it's a really exciting time to be seeing this coming all together, and I'm really fortunate I get to work on this. So before I sort of get more into the details about Roman, I would be remiss if I didn't talk about Nancy Grace Roman herself, just in case no one or anyone's unaware. Uh, she was NASA's first chief astronomer. She's also the first female executive at NASA. She's sometimes called the mother of the Hubble Space Telescope because she was one of the main proponents to getting Hubble launched. So truly, she was able to convince not only her peers in the astronomy community, not only the general public, but also Congress and the US government to get behind and support funding the Hubble Space Telescope. And um, we really have her to thank for the launching of Hubble. So in her honor, they have named the Roman Space Telescope after her. So as I mentioned in my intro slide, Roman is NASA's next astrophysics flagship mission. It's launching no earlier than October of next year and no later than May of 2027. It'll be going out to L2, and this is extremely crucial because it will have access to over half the sky at any given time. This is the same orbit that the James Webb Space Telescope is in. Roman has a 5-year minimum mission lifetime. Roman is being designed, though, to hopefully last at least a decade, if not more. Despite Roman going out to L2, it does have the capability to be serviced in the sense that it has the opportunity to be refueled. So if NASA wanted perhaps to fund a future robotic mission that could refuel Roman and extend its mission lifetime, it potentially could. So this is something that's pretty cool, is that that's really the only expendable on board is its liquid fuel. So really, otherwise, it could go on for much longer than its 5 or 10 year lifetime. Roman has the same primary mirror size as the Hubble Space Telescope, 2.4 meters. But as I'll talk about a little bit later, Roman has extremely impressive field of view. Its focal length, its F number is roughly half of that of the Hubble Space Telescope. It also has a very massive focal plane array on its primary instrument, as I'll show in a second. The Roman actually has 200 times the field of view of Hubble and 100 times the field of view of the James Webb Space Telescope. So Roman can do Hubble quality science 1,000 times faster thanks to its larger field of view, thanks to it being at L2, so it has access to half the sky, or really over half the sky at any given time. Also, thanks to its comparatively faster slew and settle times. The Roman is truly going to be a survey workhorse. It'll be really looking at the infrared skies between about zero point 0.5 to 2.3 microns, and it'll be answering three major science themes. It'll be doing that general astrophysics that could be provided by a large photometric and, in some cases, spectroscopic surveys. It'll also look at the expansion history of the universe and the growth of cosmic structure, doing a lot of cosmology. And something near and dear to my heart is that Roman will be searching for new populations of exoplanets. And it's predicted that Roman could discover hundreds of thousands of new exoplanets. And a reminder, we know of about 6,000 today. So over two orders of magnitude more exoplanets will be discovered by the Roman Space Telescope. So I really love this infographic. It's really information rich. At the left-hand side, we have Hubble and Roman, again, the same size primary mirrors, but Roman again has that larger field of view. And then that's compared to Webb. Webb has about a 6.5 meter primary mirror, Roman and Hubble 2.4 meters. So while Webb has that larger aperture, it's able to achieve higher precision, but it's a narrower field of view. So as we're showing here on the screen, here's roughly the field of view for Webb and Hubble, and outlined here in white is the field of view of Roman on its primary instrument, the wide field instrument. So the way I really like to think about it is that Roman complements both Hubble and James Webb because, for example, James Webb it has a giant aperture, smaller field of view, but it can go very deep. It can go very detailed in terms of its precision. So Roman, on the other hand, can go wide. So Roman sort of gives us that context to the James Webb and Hubble observations that are going to be taken and have been taken before. So Roman is kind of like our fisheye lens, and Hubble, or sorry, our Webb is sort of like that zoom lens. Also, Roman won't be replacing the Hubble telescope because we need Hubble because it gives us access, very crucial, unique access to ultraviolet wavelengths of light. And that's very crucial, for example, for studying stars and their activity cycles as well. So, right here is a great graphic because in the background is a mosaic of M31, the Andromeda Galaxy. It took, this was actually taken by the Hubble Space Telescope. It's with C3 instrument. And this took about over 4 years for Hubble to survey. There's actually a press release, I think, last month, uh, almost a decade or two later, where they were able to complete the entire mosaic of M31. The impressive thing about Roman is it could do this again, but only in about two pointings. So what would take Hubble months or years to do, Roman can do it in a matter of minutes. In fact, in the first year of Roman operations, it will do science that it would take the Hubble Space Telescope about 1,000 years to complete. But again, it doesn't replace Hubble. Hubble gives us that ultraviolet access, and James Webb gives us access to longer wavelengths into the infrared. So as I mentioned before, there are two instruments on board Roman. There's the wide field instrument. This is our primary instrument. It's made up of 18 H4RGs. These are Mercad Telluride detectors made by Teledyne. These are based upon flight heritage from H1 and H2RGs that are flying Hubble and James Webb respectively. And they give us, in that sort of mosaic pattern, as we see here, there's 18 H4RGs, and they're sort of up in that interesting sort of space invader upside down smiley face, if you will. It gives us, it's to avoid basically vignetting by the primary mirror. So it's a line where the optical throughput is increased due to missing the edge of the primary mirror and vignetting there. But it gives us that very large field of view, about as large as the size of the full moon. And again, the Roman wide field instrument will be doing imaging or has the capability of doing imaging and spectroscopy between about half to 2.3 microns. Um, the Roman wide field instruments, its operations have been completely driven, and really Roman as a whole has been completely driven by the community. So there have been numerous calls for science pitches, for white papers, and this has all been sent off to basically working groups of these core community surveys to focus on major science capabilities and expanding the science capabilities of the Roman Space Telescope. So this is a bit different than how Hubble or James Webb have done, which is typically like a classical observatory where you'll write a proposal and you'll be awarded time to pursue a science theme. With Roman, most of the science, about 80% or so, will be designated and dedicated for these core community surveys. So there's a galactic bulge time domain survey, there's a high latitude time domain survey, and there's a high latitude wide area survey. All three of those groups put together a report where they outline their science and they basically summarized all the white papers, all the science pitches, brought their own expertise to play as well. And they then submitted it to our Roman Observatory Telescope Allocation Committee, our ROTAC. And the ROTAC reviewed these proposals effectively by these three groups. Each of the three groups had a small, a medium, and a large ask for time. And the ROTAC is meeting, or has met, I think, and they'll hopefully be releasing their report very soon. So hopefully within a matter of weeks, if not sooner, we will have the output from our ROTAC that'll be designing or really telling us what survey designs were selected. So very shortly, we'll know literally what the Roman Space Telescope will be spending its time observing, how much time the instrument modes, spectroscopy, or imaging. It's a really exciting time for us on the project science team. Mhm. So that's its primary instruments. Most of the time within Roman's mission lifetime is going to be using WFI. There's also a second instrument on board, which is our chronograph instrument. And this is a technology demonstration. What it's basically doing is it's going to be taking the technology that's been used so successfully on large ground-based telescopes for direct imaging using adaptive optics or using EMCCDs, which have very low read noise, or using interesting and novel post-processing techniques. And it'll be applying to the first time ever in space. So direct imaging has been done by James Webb and Hubble. They haven't had purpose-made chronograph masks like we'll be using for Roman. They don't have adaptive optics that we'll be using for Roman as well. The Roman will be the first time that these ground-based technologies, these next-generation technologies, will be ever demonstrated in Earth, in space. Our sort of threshold requirements that we're aiming for is achieving a contrast of 10 to the minus 7 between 6 and 9 lambda over D with an SNR of 5 at 573 nanometers. Roughly what this capability will enable us to do is to take images of true Jupiter analogs. As I'll talk a little bit later today, our capability is looking at small, young, bright planets far away from their host stars, and Roman will give us that necessary stepping point to getting us to the next generation of technology to do direct imaging. So here's a picture that our amazing communications team took a few weeks ago. As I mentioned, Roman is being built right now in the clean room at Goddard. If you were to go today, you could actually see the spacecraft integrated payload assembly. That's this on the left. At the top, we have our optics, our secondary mirror, our primary, this sort of jungle gym erector set looking thing. That is our instrument carrier that holds both WFI and the chronograph. And then below that is our spacecraft bus, which holds things like the hard drives, the star trackers, the reaction wheels, and also our propellant. This is sort of turned around counterclockwise. This is the wide field instrument. You can see the radiators out here into space. And then on the other side is the chronograph instrument. For scale, there's some humans. So this is pretty tall. If you've ever been to the Goddard clean room, when Roman is all put together and its deployable aperture cover, its sun shield is deployed, it'll actually be taller than the door out of the clean room. And the chronograph is roughly the size of a baby grand piano. So I always forget how truly massive these instruments are. Not in this picture are the outer barrel assembly with the solar panels and the deployable aperture cover. That's actually in our TVAC chamber right now being tested. Next up for both of these pieces of hardware, the skip of the spacecraft integrated payload assembly and the OBA DAC SAS, they'll be going separately onto the Vibe chamber, onto the Vibe plates. And that's to make sure that Roman and its components will survive launch. Then skip it will head into TVAC. Then everything will be put together. So in the next few months, it'll look like a finalized, finished observatory. And then Roman as a whole will be vibe tested again. So lots and lots of testing to make sure everything is working before Roman is launched out into space. So, given this audience, Roman will be doing really interesting infrared science. And if you do any sort of infrared science, you will likely use Roman sometime in your career. But given this audience, I'm focusing here on the exoplanet cases. Um, but before I do, I would also like to mention that one thing that I'm really excited about the Roman Space Telescope is that all the data will be immediately public. So any of you can get the data as quickly as I can on I'm on the project science team. So anyone in the world can grab this data. All of it will be immediately made public and available. Um, so as I mentioned before, Roman will be an exoplanet discovery machine. It'll discover potentially hundreds of thousands of new planets. One method that I'll be using is the microlensing method. And just in case if you're not familiar with this method, we're looking at a background star. If we're lucky, sometimes a star in the foreground will pass in front, act like a magnifying lens, and focus the background star's light on the Earth, causing the background star to appear to get brighter. And if that planet is hosting if that host foreground star is hosting a planet, good Lord, you'll see a little tick up in brightness as well. So you'll get a focusing of the background star's light, both from the star and also the planet that it's hosting. See if you look really closely right there is the secondary little blip of where the light is increasing from the planet itself. So this method is extremely important because this enables us to unlock a parameter space of planets that we haven't had access to before. So when we're discovering these 6,000 planets, a majority of them are discovered using the transit method. I think over about 4,000 have been discovered so far. Most of these planets are hot Jupiters or super Neptunes, objects that are big, so they have larger signal, but also that are closer to their star. So it's easier to get follow-up observations of these targets. So that's what I'm showing here in red. On the x-axis is the distance between the star and its host star in AU. And on the y-axis is Earth masses. So most of these planets that are being discovered are large planets close to their host stars via typically the transit method. And in blue is the expected discoveries by the Roman Space Telescope via the microlensing survey that will be doing through the galactic bulge time domain survey. What's really exciting about this to me is that this is sensitive to planets more akin to ones in our own solar system. So terrestrials like Venus and Earth, potentially some Mars-like planets, maybe even a Ganymede type moon, and the gas giants that are more temperate gas giants compared to what we're finding today. And the really interesting science driver of all of this is this will allow us to take a true demographic sort of census of the planets in this part of the galaxy, and they'll enable us to effectively say uh, how frequent do planets like our own in our own solar system, but also like the Earth form. So potentially this survey can teach us how likely it is that Earth-like planets form out there in space. The other method is the transit method. You're probably aware of this one, but just in case, it's where if you're observing a host star, occasionally a planet will pass in front of it, causing the star to appear to dim, and the amount of light blocked out is proportional to the area of the planet relative to the area of the host star. So you can measure how big the planet is to its host star. And this method has been used very extensively to discover most of the known planets today. So when Roman is conducting its galactic bulge time domain survey to look for microlensing planets, Roman will also effectively get for free, more or less, a bunch of transiting exoplanets as well. So with the microlensing method, Roman's expected to find tens of thousands of planets. With the transit method, Roman is predicted to observe and discover hundreds of thousands of exoplanets. A majority of them are going to be very naturally close-in planets to their host star. They can orbit more quickly, so they're easier to see, and also larger planets. Because again, the larger the planet, the larger the tip in light, the bigger the signal, is easier to see. But the third method that Roman will be using, those are is the direct imaging method. The microlensing and the transit methods, those will both be used by the wide field instruments, whereas the direct imaging method will be done and conducted with its coronagraph. So right here is a really nice animation that the comms folks at Goddard have made for Roman. And basically, this sort of gives us a quick little primer to show at a very sort of low level or really high level of how direct imaging works. So on Roman, we have these deformable mirrors in our coronagraph that we'll see in a second. All right, so the light comes into the coronagraph. We block out the host star's light using that first coronagraph mask to block the majority of the star's light. Then we block out using this stop as well, any diffracted light around the first coronagraph. And then what we do is we have these two deformable mirrors that enable us to further correct for any aberrations of starlight in the optical beam train. DMs are typically used on the ground to correct for scintillation in the Earth's atmosphere. In space, we don't have to worry about the atmosphere, but we can actually basically use them as glasses to improve upon the instrumentation and the manufacturing. It's only so perfect. So basically, you can correct for the tiny, tiny imperfections made during manufacturing. Use artificial mirrors to improve upon Roman's performance. Let's skip ahead a little bit. After all that signal comes through, we can use some interesting post-processing techniques to further amplify the signal over the noise and extract those planetary photographs. So right here is a plot that shows the comparison of the expected and predicted precision from the chronograph with respect to other prior ground-based and space-based instruments. So we have up here Hubble NICMOS, we have James Webb NIRCam, we have STIS, we have some ground-based telescopes. They've all been up here in this higher flux ratio. So these are all more sensitive to brighter objects compared to their host star. They're also typically looking at farther separations, so objects that are farther away from their host stars as well. Typically, they're looking at bright young planets that have residual heat left over that are very far, like twice the orbit of Pluto, if not beyond, from their host stars. But with Roman, we're going to be pushing both those boundaries down. We're going to be able to sensitive to dimmer objects at least 10 to the minus 7, if not beyond at separations that are more akin to a Jupiter-like orbit around a sun-like star, between 6 and 9 lambda over d, about 550 nanometers. And the reason we need Roman is because that gets us from where we are, looking at those bright young planets. It pushes that boundary inwards for looking at those more temperate, cooler planets closer to their host stars, to eventually getting us enough information to apply to future missions. So Roman chronograph is a technology demonstration for the next generation chronographs, one such as NASA's Habitable Worlds Observatory, which one of the main science drivers for that NASA's next flagship mission is to have a chronograph on board sensitive enough to get down to contrast levels 10 to the minus 10 of an Earth-like planet around a sun-like star. So this is very much Roman chronograph is paving the way for HW, the Habitable Worlds Observatory, which is currently in pre-phase A. The formulation officer just stood up here at Goddard last year, and hopefully Habitables will launch in the next 15 to 20 years. In addition, through Roman surveys, it'll naturally, and also through its infrared passbands, it'll naturally give us access to even our own solar system. So perhaps we can use Roman to not only look at gas giants in our own solar system like Jupiter, Saturn, Uranus, and Neptune, but perhaps also Roman data can be used to discover things like things out in the Oort cloud or also any NEOs as well. So truly, not only is Roman Space Telescope for folks that are doing planetary science on exoplanets, it also potentially could be used by planetary scientists to study things in our own solar system as well. So the amount of data that's coming down from Roman is intense. We'll be getting about 1 terabyte of data a day. So just for in context, over Hubble data archive of about 30 years, it had about 172 terabytes. It'll take Roman about 170 days to hit that limit already. But Roman over its 5-year primary mission will be 20,000 terabytes a day. So, sort of looking back in context, we have this amazing foundation given to us by ground-based telescopes for direct imaging techniques, for transits, for microlensing methods. We've been able to apply them over step and step and step again from NASA mission to NASA mission, be flying and using and leveraging this amazing foundation and heritage from the Roman Space Telescope. And in turn, Roman will be laying the stepping stones for the Habitable Worlds Observatory. So given we're kind of low on time, I'm happy to take any questions, but I'll leave you with this really awesome photo of the pillars of creation taken by the Hubble Space Telescope. This was truly one of the images that inspired me to become an astronomer at the end of the day. And out here is the larger Eagle Nebula image that Roman were to get. Hopefully, we'll see something amazing like this. So happy to talk more about the chronograph or pause here to answer any questions. Thanks, folks, for dialing in.
Thank you, Mr. Rob Zellum. Um, Seems like mighty important work with Roman, and congratulations to you and the team on everything you do.
I cannot. Oh, let me turn up the volume. There we go. Sorry, I muted earlier for the video. Yeah, thanks again for having me. Yeah, happy to take any questions in the 3 minutes we have remaining.
Yeah, thanks for the presentation, Rob.
Yeah.
Really interesting and informative. I was wondering, in terms of the transit photometry
Hmm.
survey that you were talking about, do you know or do you have some estimate on the number of targets that would overlap with targets from Kepler and test missions? Or
Yeah, so the transit mission or the transiting planets will be mostly coming from the galactic bulge time domain survey. So center of the Milky Way.
Mhm.
And the Galactic Bulge Time Domain Survey has sort of put forward three different options of the fields that they want to use, but largely it's a few fields below the galactic bulge and perhaps even one inside the galactic bulge. So those are planets typically are areas of the sky that are typically not sampled by Kepler or TESS. There might be some minimal overlap in TESS, but I think these will be, I'll have to double check, but I believe these will be brand new planets that we haven't discovered yet.
Okay, gotcha.
Mhm.
Yeah, I have other questions, but I don't know if
Hey,
Matthews have.
I'm gonna jump in. Yes, um, we've noticed a lot of optical errors, aberration errors, and image data errors with space telescopes like James Webb and Hubble. There's a 20-page study out there and asking how these errors are addressed through the optics and chronograph with Raman.
Yeah. So with Hubble, you had the primary mirror optical prescription was off by less than the width of a human hair. So they've launched with Pick 2 to correct for that. And then they're able to design future instrumentation to directly correct that out. With James Webb, they have the benefit of having actuators behind each of their segmented hexagonal mirrors on the primary mirror. So they can correct for that and put things better in focus. With Roman, we have focusers on board. We go through intense INT testing to make sure things are all in focus. For the chronograph specifically, there is a focuser on board, and we have these deformable mirrors as well. So you should, knock on wood, be all good to go with the chronograph. I think, Miguel, you also had another question as well in the last minute and a half.
Oh, okay. Yeah, I'll try to make it short. This might be a little bit off topic and maybe not for you, but because you're talking about the data volumes that will be
Mhm.
produced, sometimes can be quite difficult to deal with this if you're a researcher, you don't have that bandwidth, internet bandwidth, or the storage that you need. Do you know if there's any discussion of having something like a Roman cloud system
Yeah,
to do like
actually, that's
processing or something
yeah,
like that?
that's being developed right now. So, in the interest of time, look up the Roman Nexus, Nexus. That's
Uh-huh.
being led by Space Telescope, the Science Operations Center, and they're actually building cloud computing. So that's actually how we'll all interact. Majority of us will interact with Roman data is completely on AWS servers on the cloud rather than downloading them, because each individual WFI image is actually about half a gigabyte big, which will
Hmm.
overwhelm my Mac for sure.
Okay, I guess. Okay, cool.
Yeah.
Thanks.
Yeah, great question. Yeah, if you're going to Summer AAS, I think there'll be actually a workshop on it, and there's actually usually ones at the big AASs in winter as well. So there should always be
Okay.
more information about that too. You can also find it on our website. I believe we have it linked up there too.
Okay, cool.
Yeah.
Thanks so much, Rob.